Okay, so I've got that list of additional points I need to put into the grade book related to the exam. I haven't done that yet, but I'll do it today. So, other announcements. If you're already in hydraulics, you know this, but for those of you who aren't, our class on Wednesday and Friday is just exclusively going to be online. We won't have an in-person meeting in Wednesday or Friday of this week. So I'll email you the links to those lectures. I'll also post them on Blackboard. I've got a handout related to a method that we'll talk about today, which there may be some additional discussion in Wednesday's recorded lecture related to that. So all of this week we're just talking about hydrographs, and then the assignment that you've got related to hydrographs is due a week from today. So any schedule or announcement type questions that you've got? All right. So let's talk about unit hydrographs. And a hydrograph is a representation of stream response. So here's a picture that's not in your notes. I just put this slide together today. Let's say that we have some watershed, and there's enough precipitation during a 1 hour period that it satisfies all the abstractions. So that's to say, the amount of precipitation is enough to overcome the effects of interception. That's the trees and the buildings that have to get wet before any water gets to the ground. It overcomes the surface wetting effects that are required before there's surface flow. It fills up all of the local depressions and puddles and shallow depth ponds. We're talking about the effects of evaporation are taken into account. Infiltration is satisfied so that there's ponding at the surface and there's going to be runoff. So what if all of those things were satisfied and then there's 1 inch of rainfall excess? So to do that, depending on the watershed, it may just be 1.1 inches of rainfall. It could be 2 inches of rainfall. It would depend. It would vary from watershed to watershed. But what we know is that there's all of those abstractions are overcome, and there's 1 inch of rainfall excess. And so you can see this watershed has these tributaries that are all contributing to flow at a single point. And so Q is the runoff. And so this was 1 hour of precipitation and 1 inch of rainfall excess. And so we know the depth of rainfall excess, and we know the duration that that depth occurred during. Let's say that we have some hydrograph, like that this was the hydrograph. This is what it looked like when this hypothetical storm happened. Well, this is very useful information. This is very useful for us to know what is the watershed response. If we have this graph of the amount of discharge and when it happens, if the precipitation was during a 1 hour period, then sometimes it's common for us to draw the rainfall hydrograph on the same figure as the runoff hydrograph. And so if we were going to do that, let me just insert a little bar that represents the rainfall. So it would be something like this. Here's our 1 hour of rainfall. It would be pretty narrow, because if we look at the rainfall hydrograph, you know, this represents 6 hours. And so this is like 1 inch of depth, and then we had this response. What's useful about this is that if we had 2 inches of rainfall excess in the same 1 hour period, what we could do is we could say, let's just assume now that the hydrograph is double, that the same timing occurs if it's 2 inches of rainfall excess in a 1 hour period. What we're going to say is that this method that we're going to talk about today, the unit hydrograph method, just assumes that there's a linear relationship between the amount of rainfall excess and a previously established response, stream response. Or if it was half an inch of rainfall excess, then the curve would be half as tall as it is. So it looks like, you know, for this hypothetical runoff hydrograph, it looks like we're peaking out at about 14,000 CFS. So that if we had 2 inches of rainfall excess, we'd assume that there's 28,000 CFS, and then it would have the same shape. So this is the method that we're talking about today, the unit hydrograph method. It's a linear model, which is, it's a simplification. Reality is more complicated than just about anything that we can do to set up a model. But models are useful sometimes. They're not always completely accurate, but often they're accurate enough. And so we sometimes don't have to know to the nearest gallon how much water is going to come out of a watershed. Sometimes, as long as we know within 20%, that's close enough for us to size the culverts. That's close enough for us to know whether the water levels are going to go up over the road. So this unit hydrograph method is a gross simplification of reality, the idea that you could study one storm and then predict all of the future storms based on that one response that you've studied. But it's useful nonetheless. So we assume that there's a 1 unit rainfall excess. And so it could be an inch, it could be a centimeter, whatever our unit is that we're interested in. And then we have a certain duration. So it doesn't have to be 1 hour that the storm happens during, but it's just during a known duration. And then we take that known precipitation excess duration and depth, and then we can find out other storms. And they don't have to be just only the same length. Like with this method, it is possible to predict what the storm would look like if you had, what the runoff hydrograph would look like if you had a storm that was 4 hours long. Even though this was based on a storm that was 1 hour, we can find out for longer storm durations and for different storm depths what the net effect is going to be within the watershed. It's built into the method. But the starting point is a certain time and a certain known effective rainfall is just another word for rainfall excess. And so it's not that there's an inch of rain, but it's an inch of rain after all of the other abstractions have been satisfied. And so the principle is that we can extrapolate other storms that we're interested based on the one that we do know the response from. Now, there's a lot of assumptions built into applying this method. And the assumption is that during this storm that we studied, the intensity was constant. So it's a 1 hour duration, but we assume that it goes from 0 precipitation to its intensity over the entire duration. So uniformly distributed. That just means that whatever depth of precipitation occurs, we're assuming that it happened evenly during the duration of the storm. And this also assumes that the watershed is not changing. And I mean, it's, everything's changing on a geological basis. Mountains are getting taller or eroded down. But that's not what this is talking about. Watershed is not changing. What this is talking about is the original hydrograph that we generated when we did that study storm. It was a single point in time, and it may have been during a relatively, it could have been during a drought, that this one big storm came and we happened to be studying the watershed during a drought, so you're like, maybe the soil was pretty dry. Remember, this is taking into account the rainfall excess, but it doesn't take into account the timing differences. And so if the storm happens and there's a long delay until there's a peak because the antecedent moisture conditions were really dry, then future storms where it was really moist and it takes less time to satisfy all the abstractions, the hydrograph could arrive sooner. So this method doesn't necessarily have any way to correct for issues like is the watershed have worse vegetative cover in the wintertime than it does during the summertime. It's just, we're ignoring those effects and we're just applying it as is. So to understand how the method is applied over multiple hours, like if you have a storm that's longer than just 1 hour, what we have to do is we have to divide the watershed up into zones that contribute within a certain duration. So let's say that we have some watershed, and here these numbers refer to how much of the watershed is contributing to flow after how long of a period. So if it was raining over the whole watershed evenly, and it was raining for 6 hours, what this figure is saying is that from time 0 to time 1, this is the area that would be contributing to flow, just the area that's designated in 1. And why are the other areas not contributing yet? Because they're further away from the outlet. So there's some travel time involved. So this first zone is how much of the watershed contributes in the first hour. Obviously, at time 2, there's the flow from zone 1 and the flow from zone 2 is beginning to arrive at the outlet, like if the storm continues through the entire 6 hours. And at time 3, we get further and further away from the outlet, but more of the watershed is contributing to flow the longer the duration is. And so by the time it's been 6 hours, it takes 6 hours for this furthest most point in the watershed to have overland flow, get in the channel transit time, and then finally it gets to the outlet after 6 hours. And so these differences in contributing area are going to be really significant if we have a storm that lasts more than a single hour. Because what we have to do is go through a process that's known as convolution. So you probably heard the word, that's convoluted. Like if somebody says an explanation is convoluted, what does that mean?
Overly complicated.
It means very complicated, right? So what we're going to do is convolution. It's complicated, right? And I think what you're going to see is, let's just say that if we had 1 inch of rainfall excess and we got this response, it would be relatively easy for us to make a hydrograph with just these points. But what if there was a storm where in the first hour there was 1/2 inch of rainfall, in the second hour there's 1 inch, then in the third hour 1.5, then in the fourth hour 0.5. So what's tricky about this is that we've got the delay effect, but then there's multiple storm pulses that are acting over the whole watershed at different time increments. And so we're going to have to combine together and account for the delay in when the precipitation occurs and also the delay in how long it takes to travel through the network. So there will be like a combined unit hydrograph. And to combine multiple unit hydrographs together, we're going to have, this is the precipitation amounts. So this is P1, P2, P3, P4. And then these are the unit hydrograph amounts. And so U1 is 10 CFS. U2 is 100 CFS. U3 is 200 CFS. So if we have to have multiple pulses of rainfall, and we know what the precipitation pattern is and the unit hydrograph pattern is, and we want to know the combined, like the effect of multiple pulses of rainfall over this watershed that experiences delay, then this is kind of a graphical representation of the formula. In the first hour, you'll have only the runoff from the first zone contributing. So it'll be the precipitation during the first hour and the stream response during the first hour, which is that in the first hour, only the runoff that's coming from this area of the watershed. So the convolution is just that at every hour, so this is hour 1, the first column, hour 2 is the second column. So how much water gets to the outlet during the second hour? It's the precipitation amount that fell during the first hour, but is now contributing from the second zone, plus the precipitation amount during the second hour, which is coming from the first zone. So then in the third hour, you'll notice that the precipitation from the first hour is now fallen on zone 3 and traveled its way through the network. And so U3 is just the contribution that's coming from that section of the watershed that's 3 units away from the outlet. But P1 is just talking about the precipitation during the first hour of the storm. So it just shows that there's going to be a typical hydrograph shape as we have different time periods and different watershed components that are contributing all simultaneously. And so there's the sequence, and we're going to do this on Excel. There's a sequence that we set up as a spreadsheet where we have a delayed response for every subsequent hour of the storm. Let's work through the example of this. Let's say it's this response. So this is the response of 1 hour of rainfall excess in our watershed. And then this is the actual precipitation amount, but this is not the precipitation excess because we'll just assume that there are abstractions of 0.3 inches per hour. So that's the infiltration, evaporation, all of the abstractions cumulatively. Just for simplicity's sake, let's say that it's constant through the storm. So what we're going to want to do is generate the runoff hydrograph that has 4 hours of precipitation, and each one of those hours is going to have a response that looks like this. It's just that the second hour is going to be delayed by a row representing an hour. So if you've got your computer with you today, why don't you take it out, because I think this is a useful activity to kind of get a feel for how you can set up a unit hydrograph. And I'll do the same. I'm going to start Excel here. Just from a blank workbook. Okay, so what we want to have is the precipitation and the unit hydrograph. So let me type in the unit hydrograph off to the side here, and we're going to have time in hours and Q in CFS. All right, so at time 0, there's no runoff. At time 1, it is 10 CFS. At time 2, it's 100. At time 3, it's 200. Time 4, it's 150. Time 5, it's 100. Time 6, it's 50. So this is the unit hydrograph, which is kind of the baseline response from 1 inch of rainfall excess. Now, what we know is that I'm going to have the actual rainfall pattern up here. So time in hours, and then here I'll have the rainfall in inches, and then the abstractions in inches, and then the rainfall excess in inches. And I'm sorry that's small. I'll make it bigger in just a minute. Okay, so there's time 1, 2, 3, and 4, representing the first hour. So by time 1, what I mean is the time from 0 until 1. It's the first hour period. 2 is the second hour period. So the second hour period goes from 1 until 2. The third hour period goes from 2 until 3, and so on. So the rainfall is, first there's half an inch of precipitation, 1 inch of precipitation, 1.5, and 0.5. I'm just going to underline bold it. All right. The abstractions are constant at 0.3 inches during each hour increment, and so the rainfall excess will be the difference between the two. Okay, so the rainfall excess is the rainfall amount minus the abstractions. Okay, so that means in the first hour there was 0.2 inches of rainfall excess. In the second hour there's 0.7, and the third 1.2, then 0.2. All right, so now we're going to make our hydrograph. And it's going to have time and runoff. And this is going to be CFS. Okay. And to the right of that, I'm going to have our first hour, our second hour, third hour, fourth hour, fifth hour, sixth hour. And you'll see why in just a moment, because the total hydrograph is going to be the sum of many different hydrographs together. And so here the time goes from 0 to 1 to 2. It's going to, let's say, take it down through 29 hours. So just to zoom out a bit so you can see the full perspective of the spreadsheet. So far I've just got the time of the hydrograph. I don't know the runoff, but conceptually what we're going to be doing is combining things together. So let me paste this just as kind of a conceptual reminder of what is being built in this spreadsheet. All right, so this is what happens when there's 1 inch of rainfall excess. So in the first hour, we only have 0.2 inches of rainfall excess. So it's going to be less water than this coming out of the watershed, because this is what you get from 1 inch. Unit hydrograph, this is the stream response from 1 inch of rainfall excess. Okay, the first hour we didn't have a full inch. So it's going to be 0 runoff at time 0. What is going to be the flow rate that we see at time 1? If it's 0.2 inches of rainfall excess that happens during this first hour, it's going to be equals this amount of rainfall excess. And I'm anchoring the reference here by pressing the F4 button. And then I'm going to multiply it by here. And so 2 CFS. And that makes sense, right? If in 1 inch of rainfall excess we saw 10 CFS, so 1 inch of rainfall excess causes 10 CFS of outflow, then 0.2 inches of rainfall excess should cause 2 CFS of outflow. Does anybody have questions so far? It's just linear, a linear response. And so if I drag this down through all of the hours, it's always 20% of the unit hydrograph. So 20% of 100 CFS is 20 CFS. 20% of 200 CFS is 40 CFS. And then at time 7, there's no more water coming from the first hour of rainfall. So the first hour of rainfall goes through the system like that. And that first hour just gave us 0.2 inches of rainfall excess. And so this is what happens. This is like looking at the outlet if there was just that first hour of precipitation. Now for the second hour of precipitation, let me underline this just to make it clear that these are headings rather than numbers we're going to do math with. Okay, now the second hour, we're going to use the same kind of idea, but we have to delay it by an hour because it happened, this precipitation happened during hour 2, not during hour 1. So I'm going to put in a 0 to begin, and now it's going to be 0.7, anchor the reference, times, and starting here at the top. So we should see 0 for the first hour, and then it goes down to 35, and then it's just 0 from that. So the key thing to remember is that we have to start the sequence an hour later than the first one did. So this had 1 0, which corresponds to time 0. This has 2 zeros before we see this, the first effects of runoff, because it's the rainfall pulse that begins at the end of the first hour and goes through the second hour. Okay, so the next one is going to be a 0 and another 0, and then we'll say 1.2 inches of rainfall excess, anchor that reference, and start multiplying it by the unit hydrograph. So we'll see 3 zeros before we have the first flow. And then just a bunch of zeros after that. Okay, let me pause for a second. Does anybody have any questions, or is there something that you need to see again?
Is there a reason why you're typing in the zeros instead of just taking the formula all the way down?
Well, since there isn't anything in these cells, I don't know. I guess, let's see if I do continue dragging it all the way down, what it would do. I guess it still does return 0, but it's referencing an empty cell. And if I put something in there, like if later on I put the number 55 for some reason, then all of a sudden that would give me a number. So I guess it's probably just to make sure that it actually returns as 0, because I don't want it referencing just some random cell in the spreadsheet that's empty now, but maybe it won't always be empty. Okay. So obviously for hour 4, we're going to do the same thing. Okay, so we're going to have 0, 0, 0, 0, and now we have the 0.2 inches of rainfall excess, anchor the reference, multiply it by our unit hydrograph. Did I put in too many zeros? Let's see. Yeah, I think I did. I think I put in too many zeros. It's easy to lose track of. So it's here that it starts. Okay. All right, so now let's check the end of the hydrograph to make sure that we have the last evidence of runoff is staggered by an hour each time. So 10 would be the last time for the first pulse, 35 is the last outflow for the second pulse, 60, 10. All right, so there's just 4 hours of rainfall excess. I don't need the 5 and the 6 for this one. And it looks like the last runoff is after 11 hours, and so I don't need all of these ones. Okay, so the resulting runoff hydrograph would be the sum of everything to the right. So this is just from 1 hour of rainfall, and the net runoff hydrograph is the sum of all of these. So I'm adding together everything that's to the right, and then if you drag that equation down, you'll see here's the combined runoff hydrograph. And so this has, like for any particular hour, for like hour 4, look like what it's adding together. We have the 4th hour of rainfall arriving finally, zone 4 from the first hour of rainfall. This is the zone 3 and the second hour of rainfall, zone 2 and the third hour of rainfall, and zone 1 and the first hour of rainfall. So this is the process of convolution. And then we could, if we wanted to do a net runoff hydrograph, then what we would graph would be the combined. We just draw a figure here. So let me select the data. We've got on the x-axis time. On the y-axis is the runoff. And here's our hydrograph. Runoff in CFS. and then here is time in hours. So what we took was a unit hydrograph, and we found out how would the watershed behave in a storm that has not just constant rainfall, but varying rainfall. And you have a homework problem that's similar to this, except for that I give you the precipitation amount in 4-hour blocks. And so you're going to have a lot of columns, a lot more columns, because here each one of these columns represents an hour. So in the homework, it's like, what if I said that it actually rained 0.5 inches per hour for 4 hours? So then you'd have 0.5, 0.5, 0.5, 0.5. But then, you know, you'd have the delaying effect, as is shown here. And then if for the next 4 hours it was raining for an inch, then you'd have column 5, column 6, column 7, column 8. And then you'd have like further delays as you worked through the hydrograph. This is the unit hydrograph method. Any questions about either the theory of how the unit hydrograph works or the function as we set it up in a spreadsheet? So what we did was we subtracted out the abstractions and found the rainfall excess, and then we used the unit response, and each hour it's a row lower. So here in the spreadsheet, for each subsequent hour we kind of offset where the response begins by 1 row. So here's what the equation, like if we were going to go through our spreadsheet and see what is the flow rate at any given time, you can see what part of the watershed is contributing at a given time and which pulse of rainfall is arriving at the outlet at a given time. What's really tricky is, this is called convolution. Deconvolution is creating the unit hydrograph when what you have is the precipitation and the runoff, the Q. And so you can determine U from a storm of more than a single hour, but it's a complicated process, and we won't do deconvolution. We just will do convolution. Unfortunately, we don't have unit hydrographs most of the time we want to predict the stream response. We have it for some, and we could go out and do a unit hydrograph. Like if you've got plenty of time, you can take a rain gauge into the field, you can take a stream gauge into the field, and you can prepare a unit hydrograph. But there are some cases where you don't have months to study the watershed, and you have to know today, or be able to predict today, what the response is going to be like. And so we can synthesize our own unit hydrograph using physical parameters of the watershed. And so the synthetic unit hydrographs basically are a way of looking at the area of the watershed, looking at how long the streams are, the slope, other physical characteristics that would give you a sense for what the response is going to be like when actual data is not available. And Snyder's method is the one that we're going to take a look at. And what the Snyder synthetic unit hydrograph method says is, let's analyze what's called the time lag between the middle of the rainfall pulse and the center of the peak of the rainfall. And so we're measuring if this is the precipitation and then this is the hydrograph. The Snyder method assumes that you have a triangular unit hydrograph. And why triangular? It's because we want to have some control over this tapering leg where the flow is decreasing. Normally it will take longer for the flow to go back to baseline than it took for it to go up towards its peak. So here it's saying that the time to go back down to 0 flow rate is twice as long as the flow increasing up to the peak flow rate. And so there's these physical constituents where we have a dependency on the area of the watershed, how long the main channel length is, the distance from the outlet to the watershed centroid, and then there are these curve fitting parameters that are based on just other watersheds in the area that have been calibrated. You can have these coefficients that go into the method, and you use this to create what a unit hydrograph would look like if you have storms of either an hour, or you could actually make unit hydrographs where the storm duration is less than an hour. Let me give you this handout because it has the step-by-step process. Okay, so this has the steps that you should go through, and then it also has my calculations in the subsequent pages, just kind of illustrating how you would find out the unit hydrograph. This is assuming a watershed that has an area of 5.42 square miles. The length of the main stream is 4.45 miles, and then the length from the watershed outlet to the point opposite the center of gravity is 2 miles. So center of gravity is just, they mean it in the same sense of center of area for the shape of the watershed. So it's the regional coefficients of 2 and 0.625. So the steps here, it shows the formulas for calculating different components of this shape. The main things we want to know in the unit hydrograph is what is the peak runoff, so how much flow is there going to be at the peak, and then how long is it going to take to get to the peak from the start of the storm. So what we're most interested in is how much flow is there going to be, how long does it take from time zero to the time to that peak, and then we're also interested in how long until it gets from peak flow back down to zero flow. So this handout walks you through that. We won't take the time to do the calculations now, but are there any questions about unit hydrographs in general or the need for a synthetic unit hydrograph? Any questions before we finish for today? All right. So if you haven't already, take a look at that hydrographs assignment. It has a synthetic hydrograph problem like the handout that I've just given you. It's got a unit hydrograph problem similar to the example that we just worked in class today, except for that there are 4-hour blocks of the precipitation. So let me just be naughty and show you the solution, because this has been an issue enough times that I think just a quick glance at the solution would be justified. All right. So I think this is the one, yeah. It's 4-hour time blocks, so you're going to actually have 16 columns because the rainfall amount is constant during P1, P2, P3, and P4. It's the same amount of intensity during that entire time period, but you're going to be lagged and offset by an hour with each column. So It'll be 16 columns wide, but then the total runoff hydrograph is the sum of all the columns that contribute to the precipitation at any given time. So that's your peek at the solution for the unit hydrograph. It's going to be really wide, but once you set up the unit hydrograph and the kind of header details like we had here, these amounts, then it doesn't make it that much more complicated to have the 4-hour blocks. All right. That's all I got for you today. Remember to look in email or on Blackboard for the links to the lectures on Wednesday and Friday. And I'll see you back in class in person a week from today.